All right, so today we're going to be talking about ionic bonds. So the first thing we're going to do before we really jump in is cover two main base concepts that we're going to be using throughout. The first one that we're going to be covering is the octet rule, basically stating that every atom wants 8 electrons in the outermost energy level, also known as 8 valence electrons. Valence electrons. Now, there's a couple quick exceptions I just want to throw in. We'll do some quick exceptions. Usually hydrogen, helium, lithium, and beryllium will settle for 2 valence electrons, and we call this the duet rule. Duet, do meaning 2, like oct means 8. It's pretty easy to see where these names come from. Basically, what this looks like in practice is if we take fluorine, and actually I've been doing fluorine in class. Let's go ahead and make it a little crazier. Let's take oxygen. Now, oxygen has 8 protons and 8 electrons. So if I were to draw a Lewis structure for it, I'll put a little +8 in the middle, or a Bohr model, my apologies. So let's start out with our 8 electrons. So I'll go ahead and draw 1, 2, 3, 4, 5, 6, 7, 8. So oxygen wants 8, and currently it has 6 valence electrons. So what it's going to do is take 2 valence electrons and plop them right on. And what we will end up with, gotta grab that one. What we'll end up with is this oxygen with 8 protons and 10 electrons. However, now it has 2, 4, 6, 8 electrons filling the octet rule. Now, one crucial aspect is that now that it has gained 2 electrons, it will be a 2- charge. And we can kind of just figure that out by taking 8 minus 10. And that gives us our charge of 2-. So if we were to represent this element, we would say O2-. And then one more keynote is that we now call this oxide. Right here, this IDE, the suffix IDE. We use this suffix whenever we have an anion, which is basically just a negative ion. Remember, ion meaning charged atom. So that's how an element like oxygen would fulfill the octet rule. It would become oxide, picking up 2 electrons and picking up a -2 charge. So we'll say here it gains 2 electrons. All right. So the next one I want to go over is we'll pick something a little crazier too. We'll pick something that really demonstrates it. Let's go over aluminum. Now, aluminum has 13 electrons and 13 protons. So if I just go ahead and draw it right here, I will have a +13. And I know that aluminum being in the 3rd period will have 3 energy levels. Oh. And I'll go ahead and draw its electrons, 2 in the 1st ring, 8 in the 2nd ring, and 1, 2, 3 in the 3rd ring. Now, aluminum also wants to fulfill the octet rule. And you might think, oh, well, it's already got 3 it already has 3 valence electrons. What if we just add 5 more? Well, the problem with that is adding 5 electrons is really hard. As we continue to add more, they're just going to repel each other. So adding those 5 is going to be really hard. So we're not actually going to do that. Instead, what we can do is we can just say goodbye to 1, 2, 3 electrons. And we end up with this nice aluminum that now has 1 less shell and 3 less electrons. So what we're going to do here is lose 3 electrons. And then we get this. Because we have lost 3 electrons, we now go to 13 protons still and 10 electrons. So our net charge is going to be 3 plus. And we'll call this Al 3 plus. The other thing is before, when oxygen gained 2 electrons, getting a negative charge, it became oxide. On the flip side, aluminum will stay aluminum. No change in name for cations or positive ions. We'll call this a cation or positive. The quick, easy way to remember this is that cation is positive because cats have paws. So even when you watch my video lectures, you cannot escape my terrible jokes. But if you remember that cations are positive, then you will remember that anions are the other one. So if positive's taken, anions have to be negative, just process of elimination. One quick thing to look at is when we are looking at valence electrons, if you have 1 valence electron, you could either lose the 1 or gain 7, and just always go with the option that seems like less work. Atoms are lazy. Losing 1 versus gaining 7, you can think of it as 1 homework problem versus 7. You're going to pick the one that has less. One more quick thing I just want to point out that I almost forgot about is the reason this works up here, the aluminum, is when we lose our 3 electrons, we're actually deleting that whole outer shell. It all goes away. And when it all goes away, we still end up with 2, 4, 6, 8 electrons on the outside. The outside has just changed from the 3rd energy level to the 2nd energy level, or the 3rd ring to the 2nd ring. So we're still fulfilling the octet rule here. Octet rule is fulfilled. Octet, hooray. So just keep that in mind. So like if we looked at maybe phosphorus with 5 valence electrons, there's 2 paths to 8. We could lose 5 and reveal the ring underneath like we did with aluminum, or gain 3. And here we're still talking about electrons. And again, we'll pick the one that has less steps to it. Gaining 3 is less than 5, so that's what phosphorus is going to do. So that's the first major part of ionic bonds. It is the octet rule and how we fulfill it in every atom. So with that said, we're going to move on to the next part, which is going to be Lewis dot diagrams. And these are pretty basic. There's 2 main rules. One, we want the element symbol. And 2, we want the number of valence electrons. Now, the way we show that is with dots. We use dots to equal a valence electron. So if we take the atom, let's say magnesium, Mg. Mg has 2 valence electrons. If you're saying, Mr. Garcia, how did you get that so fast? Well, there's a really easy way. We look at our periodic table. Magnesium is in group 2. Oh, magnesium's in group 2 right here. Therefore, it has 2 valence electrons. If I scooched on over, well, here's the first big thing. We're going to forget the transition metals for now. I'll use a color that will actually show up. Forget the transition metals. And we're just going to look at the main group elements. So what we can see is if we just take whatever the group number is for at least 1 and 2, these all have 1 valence electron. Group 13 has 3 valence electrons. Group 15 has 5 valence electrons. Group 17 has 7 valence electrons. So for these back here, it's just group minus 10. And here it's just a group number. Group number minus 10 on the right, group on the left. So back to our problem of magnesium. It's got 2 valence electrons. So the Lewis dot diagram is 1. We're going to put our element symbol, magnesium, and 2. We're going to put 1 dot for 1 valence electron, another dot for another valence electron, and we are done. Hooray. Want to do that in green. We are done. Bam. So let's go ahead and take one that we just talked about too. Let's say phosphorus. Phosphorus is P with 5 valence electrons. So I'm going to go ahead and put 1, 2, 3, 4, 5. All right, there it is. 3 valence electrons. Hooray, we did it. So a couple quick rules with this. First off, if we look at any element, let's say element X, if you imagine a box around it, electrons go on the sides of the boxes. Electrons go on the sides of the boxes. So let's pretend element X is now neon. So I'm going to go ahead and write Ne. Neon is a noble gas with 8 valence electrons. So I'm going to put my electrons on the sides of the box. 1, 2, 3, 4, 5, 6, 7, 8. And I have gone ahead and made that box. So one very important thing, you'll notice that I am putting them in a clockwise order. And I'm doing it one at a time. This ensures that my electrons are as spread out as possible. Electrons are spread out. Because the key aspect here is that lone electrons participate in bonding. So lone electrons participate in bonding. Here I have 1, 2, 3, 4 pairs of electrons. These are pairs. Therefore, they do not participate in bonding because I said only lone electrons do. So if we go ahead and look at magnesium, magnesium has 1, 2 electrons that bond. Those are lone. And if I look at phosphorus, it has 1, 2, 3 lone electrons. So these are also lone. So phosphorus can make 3 bonds. Magnesium can make 2 bonds. And our good friend neon over here can make 0. Oh, how did I switch to blue? Can make 0 bonds. All right, so that is the important part about Lewis structures. One at a time, I do it clockwise. Electrons are spread out because lone electrons bond. So we have set up all the groundwork. Let us go ahead and actually do an ionic bond. But wait, there's more. First thing, a dumb definition. An ionic bond is a bond between ions. Remember, ions are charged atoms. So any atoms that have a difference in protons and neutrons. So if we're going to define this even further, protons does not equal electrons. I've been saying neutrons. Protons does not equal electrons, therefore there is a charge. So one more final aspect is ionic bond involves a transfer of electrons. They are not shared, but instead they move from one atom to another. So let's take an example of sodium plus chlorine. Sodium plus chlorine. So first things first, we're gonna write Lewis diagrams. So let's take sodium Na. It has one valence electron, so it's 1. Then oh, you know what? I'm gonna go ahead and actually color code these for once. Sodium Na has 1 electron. Chlorine Cl has 1, 2, 3, 4, 5, 6, 7. If we do a quick observation, we can tell that chlorine has 1 bonding electron. Sodium has 1 bonding electron because those are the only 2 lone electrons. So they're going to share. Now, if sodium has 1 valence electron, if we looked up back at our notes previously, if we have 1 valence electron, we have 2 ways to get to that full shell. We can reveal our beautiful inner shell of 8 by losing 1 electron, or we can create a new shell of 8 by gaining 7. Sodium is lazy AF. So sodium is going to ditch that electron. It's going to lose the electron. Chlorine, on the other hand, has 7 valence electrons. We can pretty easily see where this is going. Chlorine wants 8. So chlorine is going to find a way to gain an electron. And if sodium's losing an electron and chlorine's gaining an electron, we can see what's very clearly going to happen. So number 2, we will transfer electrons. So Na becomes Na plus because it lost an electron. Chlorine becomes Cl minus, but now we got to draw those electrons. Chlorine has still the 1, 2, 3, 4, 5, 6, 7. And sodium's 1. They both fulfill the octet rule. We have a cation over here. We have our cation. We have our anion. So the real big question of this lecture that I'm going to throw in right now, why will these bond? What's bringing them together? What's bringing this positive sodium and this negative chlorine together? Well, same thing as what we see with the protons and the electrons in an atom. The answer for pretty much everything is going to be Coulombic forces. A positive and a negative attract through Coulombic forces. So that's the star point of this lecture. So what we'll do is we'll see what happens next. Well, first things first, we can write the chemical formula. So the chemical formula is just the element symbols with subscripts that represent the ratio of each element. That's a lot of fancy words for saying if we have 1 sodium and 1 chlorine, the ratio here is 1 to 1, which means our chemical formula for sodium chloride is going to be Na1Cl1, a 1-to-1 ratio. But before you get all uppity, we're actually going to instead write NaCl because scientists are lazy and we do not like those ones. I'm actually going to just go ahead and cross them out. If we don't have a reason to write a 1, we never will. We'll just always assume there's 1 unless someone tells us otherwise. So the formula is sodium chloride, or NaCl, which we then call, my bad, sodium chloride. Why is it sodium chloride and not sodiide chlorine or sodiide chloride? Well, that's easy because I already showed you somewhere up here. There it is. Cations to the positive one stays the same. Aluminum stayed aluminum. Well, anions, the negative one, changes to IDE, and that is just this convention in science. So sodium positive stays the same, chlorine negative becomes chloride. Now, I'm going to show you one more example. This one's straight from your book. If we have magnesium and, well, I'll change it a little bit, and fluorine, magnesium and fluorine. So I'm going to start out by writing out these elements. This is an example. Magnesium has 2 valence electrons. Fluorine has 1, 2, 3, 4, 5, 6, 7. Remember, you can get this from the table. If I go back up to my table here, fluorine has 7 and magnesium has 2. So we want to fulfill the octet rule. So magnesium is going to lose 2 electrons. All right, so magnesium is going to become Mg2 plus because it's lost 2 electrons. And we just have these 2 electrons here. They came off magnesium. Where do they go? Well, one of them is going to go ahead and find its place right here in fluorine. And now we have magnesium. This is going to fulfill the octet rule, and this is going to fulfill the octet rule. Fulfill octet rule. But the problem is we still have one more electron. We have 1 extra. What do we do with it? Well, we just say if there's 1 fluorine, there's got to be another one. So let's add another fluorine. That one will go right there. And now that also fulfills the octet rule. So all we did is we added 1 more fluorine. So now if we look at our chemical formula, first off, both of these fluorines are going to be minus. And second off, our chemical formula is going to be Mg. We won't write the 1 because there's only 1 and scientists are lazy. F2, MgF2. And that's it. The last example I'm going to show you. So this is final example. This is going to be how to do an easy, super easy cheat way of figuring this out. So we're going to do aluminum and oxygen, the first 2 elements that we had when we were doing the original, what's it called? Octet rule. So aluminum has 1, 2, 3 valence electrons. Oxygen has 1, 2, 3, 4, 5, 6. So we can tell that aluminum will lose 3. It will be Al3 plus. And oxygen wants to gain 2. It will become O2 minus. So if we want to find the quick way of finding the chemical formula, we're just going to rewrite these symbols, Al and O, and we're going to write them next to each other. And then how do we figure out how many of each go together? Well, we can keep adding whichever one is in excess until we figure it out, or this is what I call the crisscross method. Take the 2, criss, take the 3, cross, and this becomes this becomes Al2O3, and our chemical formula becomes Al2O3. You just take the charges and swap them. So that's all I have for you tonight. Please rewatch, slow down, speed up, whatever you need, and have a great night and day and semester. Bye.